defining what a critical spare part is, the holding levels required. We'll talk about different spare parts holding locations, for example, on-site compared to an off-site warehouse, and then finally compared to the manufacturer. We'll then be putting this information into a simulation package that will help us do some predicting over time, that will give us the spare parts usage as well as budget. It'll predict the optimum holding level at each one of those locations, and then lastly talk a bit about bill of materials and how we can use this kind of analysis to build up a bill of materials if that's not already completed. So first off, talking about where the spare parts fit in, looking at the graphic on the right, there are a lot of different things that make up a reliability professional's job. Things like doing reliability block diagrams and a RAM analysis, that piece up there on the top. We've also got maintenance strategy development and optimization, life cycle costing, root cause analysis, and that defect elimination piece. And so there are a lot of different pieces that we would consider to be in a reliability professional's toolkit. And spare parts optimization and analysis is one of the very important aspects of it. When you look at things that have or could have the potential to have a large impact on availability, spare parts is always one that comes out on top, and that's primarily due to the fact that some of the spares on site have either a high cost associated with the purchase of that item or have a long lead time, and therefore that lead time would be multiplied by the cost of downtime while you're waiting for that spare part. So spare parts are just one piece of the puzzle here, but it's a very important piece. So to go over a few definitions, we've got a couple of different types of spare parts. First, we'll talk about what we would define as an operating spare part. So this is something that's used in the course of normal operations at your facility. Things like consumables, filters, really anything that's assigned to a PM or planned maintenance in your system that is changed out on a scheduled basis. You expect a replacement and you know when that spare part is going to be needed. So that is what we would determine as an operating spare. Next, talking about capital spares. These are a bit different. These are very high dollar items. Each facility or each company will typically have a number or a threshold value that would define an operating spare part, be it $50,000, $100,000, maybe $500,000 would define a capital spare part. These are also purchased as part of a capital project as opposed to being purchased out of a maintenance budget, and they're not typically considered part of the normal inventory. And lastly, we'll talk about insurance spares. So these are not necessarily needed in the course of normal operations. They also usually have a long lead time and a significant impact to production. So primarily our conversation today will be focused around these insurance spares and determining the level of holding at each one of our locations in order to maintain a high level of availability.
Joel, we have one question from David regarding where do critical spares fit in this kind of list and this process?
Yeah, and that's a good question. Critical spares kind of spans across a couple of these different areas. We would typically determine a critical spare to be anything that has a direct and immediate impact on production. So if you didn't have that spare part when the asset failed, then production would immediately be impacted. So although we don't necessarily define it here, critical spare part spans a couple of these different categories and certainly would be in the insurance spare category that we'll discuss here today. So good question. Thanks, David. A couple of the things that we need to consider when doing a spare part optimization would be things like redundancy. So is there a duty standby pump, for example, and how does that affect production? Do you lose 50% capacity when that duty pump fails, or do you lose 100% capacity? kind of along those lines, or the switching time it takes to get from one asset to another, as well as the lead time on the spare part. So it may be acceptable not to hold a spare part for a duty standby type relationship, as long as that lead time is within the time you'd expect to repair that pump. Kind of leading on from that, is there a long lead time regardless of the redundancy? So if the lead time is just a couple hours to maybe half a day, that might be something that you can live with, compared with a spare part that has 2 days or 3 days or potentially even longer for some very custom parts that could be up to 6 months or a year. So that certainly has an impact on your spare parts holding decisions. Next, a spare part that is a low cost but has a high impact on downtime is kind of a no-brainer in terms of holding that part. It doesn't cost a lot of money in order to purchase it, but if you don't have it, it would have a very high impact on downtime. We see this a lot with instrumentation, for example, where people tend not to think about a low-cost spare part because it is a low cost, but on the other hand, it's more difficult to think about the effect it has on downtime. And this is certainly kind of an obvious situation where you'd want to hold that spare part. On the flip side, if the spare part is very high in cost, but if it does fail, there's a very low impact on downtime, that may be an area where you could afford not to hold that spare part because you're kind of freeing up cash and not holding the spare and not incurring those spare part storage costs, when if that asset fails, it really wouldn't have an effect on downtime anyway. And then the last item for consideration are frequent unplanned failures. So it's one thing if the failure is mitigated by a planned task and therefore you can plan for the replacement of it, but if it's something that occurs without warning and it occurs very frequently, that again is a spare part that would have a high consideration for keeping on site. Now all of this stuff we've talked about kind of subjectively up until this point, and eventually we're going to transfer into these subjective decisions and pushing them into more of a quantitative type realm. So assigning numbers to downtime, assigning a cost and a delay time, and using a simulation technique in order to figure out the optimum overall holding level in order to reduce overall cost. And that cost being both the cost of purchasing it, the cost of storing it, and then probably most importantly, reducing the cost of downtime to the plant. So when defining the spare part in terms of quantifying it, the cost is probably the most obvious. So how much does that spare part cost to purchase? The next thing we'll define are the different storage locations in which you could potentially have that spare part available. So to make things simple, or to use an example here, we'll just say that there is an on-site warehouse right at the facility where that part is used. Secondly, we'll have an off-site warehouse that is some delay to get to the on-site warehouse. And then lastly, the manufacturer. And we'll say that the manufacturer is always going to have enough required spare parts, but there may just be a long delay time to get from the manufacturer to the on-site. So for each one of these locations, we'll be defining a delay to get the spare part from that location to the job site to make the repair. The next aspect is the cost of storing that spare part. So the purchasing is one thing, but just to have it sitting on the shelf costs the organization some kind of dollar amount, and that's paying the people in the warehouse, keeping the lights on, taxes for all the spares in the warehouse. Typically, we'll estimate that that cost is usually about 25% of the cost of the spare on an annualized basis. So if you consider a spare part that costs $10,000, 25% of that being $2,500, then that $2,500 is the cost to the organization every year by holding that spare part on the shelf. And then the last consideration is where that spare is used in the facility. So we'll talk about not only optimizing one spare part for one piece of equipment, but also the potential of optimizing that one spare part for multiple locations within your facility. So next we'll move into actually quantifying the decision, and in order to do this, I'm going to switch over to a software package that we use called Availability Workbench. It's an isograph software package, and it's going to help in quantifying these decisions that I discussed earlier. So up on screen, we should see the Availability Workbench software. And there's several different modules within AWB. I'll just call it that for short. So if I select these modules up here in the upper left-hand corner, RCM cost is where we do the maintenance strategy development portion of reliability, and that's actually where we'll be working for spare optimization. We also have AVSIM, which is a reliability block diagram modeling tool. This is where we would perform a RAM analysis, reliability, availability, maintainability. We can also do some work order history and data analysis using the Weibull module, then transfer that into lifecycle costing to determine, kind of how the cost changes from concept of purchasing the asset all the way through operation, maintenance, and then into disposal. Process reliability is a way of taking production data and determining where your losses are coming from in the facility. And then a couple of different portals that allow us to hook directly into various CMMS packages. So starting off in the RCM cost package here, what we've done is build up a relatively simple failure modes and effects analysis kind of in the top level of this hierarchy here. And it follows a very structured FMEA process that aligns to SAE JA 1011 and 1012. Just in terms of the 7 questions of RCM. And it also quantifies each one of those values. So built into each one of these failure modes here in the pink tile is a whole bunch of downtime, repair data, failure characteristics that will allow us to make these quantitative decisions. So the first thing I'll do is run the simulation and appreciate the fact that a bit of work has gone into this model already in terms of populating those failure characteristics and downtime data. But the first thing I'll look at here is the contribution plot. And what we're looking at are the different failure modes in the model and their contribution to overall cost. So in running this simulation, the simulation runs for 10 years. So a 10-year lifetime, and we do that simulation 100 times. So basically, through random number and Monte Carlo simulation, that will generate overall cost predictions, sum them up, and then run them 100 different times, average them out, and that's the results that we have here. So the very highest failure mode over that 10-year period contributing to cost is going to be this 2.4.A.1. So if I take a look at this failure mode, I can click on the mode and bring it up, and we'll start to get into some of the detail that defines this. So this particular one is a mechanical seal worn. That's the failure mode description. And next we'll look at what happens when that failure occurs. So in this particular case, the mixer, which is the asset we've done the FMEA on, is down. And when that mixer is down, we've got a downtime cost of $15,000 per hour. So that's a very important number because during this whole quantitative analysis, what we're doing is comparing the cost of purchasing and holding that spare part against the cost of downtime. So that $15,000 plays an important role in this analysis. Moving over to the failure tab here, this is where we define how often we expect failures to occur. And this information can come from a number of places. If you have good work order history, then you can do a Weibull analysis on that history and come up with these parameters. And if you don't, which is not unusual, you can do a facilitated session and ask some subject matter experts how often they've seen this fail in the past and what type of failure it is. So in this particular case, we're looking at a high chance of failure once you hit 3 years. And the beta value, without getting into too much detail, tells us that it is a wear-out type failure, which means it doesn't happen randomly, it doesn't happen right off the bat when you install it, but it gets progressively worse and worse and worse over time. So it's a wear-out type failure. Next, we'll move over into the maintenance tab, and these are the different types of tasks that are needed to maintain the asset. So at the moment, we'll just focus on a corrective task, which means what happens if that asset fails in the middle of the night and you need to scramble to make repairs to it. So we've got a task that's being done, replacing the seal, a duration for that task, the number of people required to make the repair, and then what we're really interested in here is this 100-673 seal. So going into the seal, I'm now in the box that's going to talk about the detail that defines the spare part. So here's our number out of the CMMS, the description, the cost of the spare part, which is $50,000. And then next we'll start to talk about where the spare is potentially located. So level 1 I'm going to define as my on-site warehouse. So this is very close proximity to the job site. So at the moment I'm not holding any there. The storage cost rate per unit is $1.50. So that means every hour you incur $1.50 of storage cost. And that's using that 25% annualized number off of 50,000. And then lastly, how long does it take to get from that warehouse to the job site? In this case, it's an hour. So level 1 is our on-site warehouse. Level 2 I'll define as an off-site warehouse. So it's not located there on site. It's got to take some kind of transportation to get it from the off-site warehouse to your job site. At the moment, we're not holding any spare parts there. It's got a slightly lower storage cost. And then lastly, it takes 3 days or 72 hours to get from that warehouse, that off-site warehouse, to the job site. And then the last definition we'll make is level 3, and that's what we're going to call the manufacturer. So here we don't have the ability to input a capacity. We're just saying they've got as many as we could ever need, but it's going to take an entire week or 168 hours to get from that manufacturer to the job site. So those are some of the things that make up our spare part. So knowing this, after reviewing that data, I know that we're not keeping any of these seals on site. There are none at the off-site location. So it's going to be a week after this asset fails before we actually get the part to the job site. So that's what's driving this high effect cost here, this high blue bar, is waiting for those spare parts. So what I'm going to do is choose a spare on the left-hand side, and we'll switch to the spare optimization plot within RCM cost. And what this is going to allow us to do is optimize the number of spare parts that we hold at each one of the locations. So we can optimize both at level 1, the on-site warehouse, as well as level 2. And we need to give it a range. So we're going to say we want to evaluate holding anywhere from 0 to 2 at the on-site warehouse, and anywhere from 0 to 1 at the off-site warehouse. So first thing we do is set up these ranges. Once that's complete, we would click the simulation button, and it gives us a bit of a profile of the options available to us now. The pink bar is going to be the overall cost of unavailability. So when that asset fails, there's that $15,000 an hour downtime multiplied by that week's worth of waiting for the spare part. And that's why we have such a high bar on the left-hand side, because this represents our current situation where we're not holding any on-site and we're not holding any of the off-site warehouse. We have to wait that full week to come from the manufacturer. Now that downtime is decreased a little bit when we start holding one off-site. So in this particular case, we're holding none at the on-site warehouse and one at the offsite. And eventually, as you go across, you can see the blue start to raise up, and that blue is our cost of storing the spare part. So the more you store, the more it's going to cost. But that is typically a pretty small number compared to the cost of downtime. So from a purely cost perspective, you'll see the recommendation there, one, which is holding one on site and one at an off-site location. So in this particular situation, our optimized spare part holding is one on site and one off site. So what I would do at this case now is accept the recommendations. And what that does is change our holding level, so we've actually got one at site and one at the off-site location. It changes those properties in the seal. And we could re-simulate this entire model again and go back to our contribution plot. And now this 24A1, which is the mechanical seal worn, is now greatly reduced because we've reduced that 1 week wait time getting the spare part from the manufacturer. So this is a good example of how we would kind of show the value and the quantitative cost benefit of holding this particular spare part both on site and at the off-site warehouse.
Joel, just there's a few questions that have come in. We'll pick out a few of them if we've got time. It appears to be pretty detailed analysis. Would you recommend performing this kind of analysis on all the spares in your warehouse?
That's a good question, and I would kind of liken that or compare that to doing an RCM analysis for everything in your plant. That's not something that we would typically recommend doing, simply because not everything in the plant is critical, and an RCM level analysis is something that you would do only on your most critical equipment, and a lower level of analysis for less critical stuff. So comparing that to the spare part optimization, it's very much the same. Because of the input required for this level of analysis, it works very, very well for critical spares, things that are high cost, have a long lead time, and you're having trouble figuring out whether to hold one or not. But in terms of a lower level critical spare or a lower critical spare, we've got different processes that we use for that. Kind of decision matrices based on the cost of the spare part, the lead time, the downtime, things like that. So to answer the question, no, we wouldn't recommend doing this on everything, but it works very, very well for the top, I would say, 5 to 20% of your spares.
Great, thanks. And one more quickly while we're here. If you had a warehouse manager that wanted to reduce their inventory for parts not used within, for example, 5 years, how would you approach that situation?
Yeah, that's a good question as well, and I think it kind of speaks to what we've just been going over. So from a warehouse perspective, their main concern is just about reducing inventory, reducing the taxes in the warehouse. They typically don't have the lead time view or the downtime view that somebody in reliability would. So us as reliability professionals, it's really our job to help educate everyone at the facility and in specific the warehouse manager to say, we understand you haven't used this part in 5 years, but there is a small chance of a failure even with our PM routine. And given that small chance of a failure, from a statistical approach, it still makes sense to continue holding that spare. And you can always put that question to them. Do you want to be the one responsible for not having that spare when we actually need it? Because from a data RCM approach, there's a chance that we'll need it, and if we don't have it, there'll be a large amount of downtime. So, okay, another good question. So I mentioned earlier that we'll talk about adding in a few other pieces of equipment, and we'll do a simple example of that now. We've now optimized the spare part and reduced overall cost of the model. So to make it a bit more complex, what we'll say is that we've got a duty standby type of arrangement for this agitator. So we're going to add in an additional spare part or an additional piece of equipment that uses that same spare part. And in order to do that, we'll add what's called a redundancy factor on this particular failure mode. So I'm going to choose the effect, which is the downtime for the mixer. And this redundancy factor, the value 1 here that you see, represents the percentage chance that we will incur the downtime. And so 1 just represents a 100% chance. Now, if you had additional components in parallel that will mitigate that effect from occurring, we can include that now. So I'm going to say that it's a duty standby, and each can take 100% of the capacity. So I'll say there's 1 additional component in parallel. We only need 1 of those 2 to be operating. And then the fractional downtime of each component is basically the unavailability of that standby equipment. So if you say that your standby pump or agitator, in this case, for example, has 95% availability, that means your fractional downtime is 0.05. So that gives us a redundancy factor of 0.05, and now only 5% of the time will we incur that effect when the equipment fails. So this is how we would set up multiple equipment that use the same spare part. So I'll click OK here. And we'll head back to the spare parts optimization and rerun the simulation. You can see our bars have changed a bit. Now, it looks like the cost of storage has gone up, but it's really just the scaling on the graph. So what's happened is the cost of unavailability has come down quite a bit. And that's because most of the time, 95% of the time, you're going to have that standby agitator ready to pick up production. So in this particular case, the storage cost is much higher relative to the cost of unavailability, and it's recommending that we hold 1 on site and none at the secondary warehouse. So this is a good example of including some additional equipment at your facility that use the same spare part. So at this point, I'll switch back to our presentation. And move into more of a quick bill of materials discussion. As part of an RCM analysis, you typically start with a location hierarchy and build out your functions, functional failures, and failure modes from there. And part of this quantifiable RCM approach that we do in RCM cost is adding the different resources required to get the equipment back into service. So in this case, we're concerned with spare parts. So for the mechanical steel worn that we were discussing, that specific spare part is then assigned to that failure mode. So the spare part then becomes part of a bill of materials, and that bill of materials is all of the spare parts included in this motor, gearbox, agitator, shaft, and agitator blades. All of the spare parts then get rolled up to the location. And because of that, now we can use the exporting features with an RCM cost to say, these are all the spare parts used in our RCM model for this location. And we can then export that into some type of load sheet that will then form your spare part as well as bill of material load sheet going into the CMMS. So this is kind of, I guess, what we call a fringe benefit from doing an RCM analysis, is that if you don't have that bill of materials already in your CMMS, you can kind of use this information to populate the CMMS. So in summary, using kind of a quantitative approach, we're always focused on the cost of purchasing and storing that spare part compared against the cost of downtime. So it's always a balancing act in trying to find the overall lowest cost between the two. Somebody in the warehouse is always going to want to reduce inventory, and somebody in Operations, for example, is always going to want to hold as many spare parts as we possibly can. And it's our view that it's a reliability professional's job to kind of look at things from both of their perspectives and find the overall lowest cost for both of those two areas. We do use a failure rate as well as the type of failure. So most failures aren't necessarily random in nature. So as part of this analysis, we define whether they're wear out, random, or fail right off the bat, such as infant mortality. Some of the other benefits you get from doing this that we didn't necessarily cover in RCM cost would be a usage profile and therefore a cost profile over time. And that's the graph that you see in the upper right-hand corner. That's our cost of spares for each year, cost of labor, as well as the cost of downtime. And that can then become kind of a zero-based budget for both maintenance and operations. And then lastly, the uploading of bill of materials into the CMMS, again, kind of a fringe benefit you get from doing from this level of analysis. So that's everything that we wanted to cover for the predicting the future spare parts analysis and optimization. At this time, we can take some questions or call it a day. So Simon,
sure, Joel,
I'll turn it over to you.
Yeah, just got a couple more questions quickly. One of them is, do you have the capability in the tool to add the costs required to maintain the critical spares on site?
The cost required to maintain the critical spares on site.
Yeah, so say if it's a spare pump and maintaining low moisture content, etc. Does that make sense?
It does. I think what I would probably say to that is we would build that into the storage cost of sparing it. So you might, the storage cost of keeping that spare part. So you might say that 25% that I mentioned, and then add on some additional costs for maintaining it.
Yeah, great. And one other one I've got here from Deepak is there benchmarking that you're aware of for spares required versus spares cost in the total maintenance cost?
Okay, so is there benchmarking that we're aware of? And what are the two numbers, Simon?
I guess it's comparing the spares cost in the spares required versus the spares cost in the total maintenance cost. We can address. I'm not sure.
Yeah, no, that's a fair question. I don't personally have that benchmarking data. There may be some that exist. The comment that I would make to that is that there are so many different variables, and this is always the problem with benchmarking, but there's so many different variables such as cost of downtime, cost of the spares, that it seems to me benchmarking that kind of information would become difficult. It might be a starting point, but when it comes to actually optimizing a specific spare, I think you'd want to do it for that individual site. But fair question.
Yeah, good, great. And one last one from Stan. Is it deemed a reliability responsibility to determine the cost of downtime?
I would tend to agree with that. Now, reliability isn't responsible for production, that's for sure. But if you look at all the different kind of areas in an organization, so purchasing, spare parts in the warehouse, operations, maintenance, reliability, safety, to me, reliability is kind of the one area that should span across all of them. Now, they don't have a reporting structure like that, but in terms of being able to talk to somebody in purchasing and talk to somebody in operations and maintenance and kind of level all of that information, include it in some type of model or analysis, and then make the decision at that level. To me, sometimes it's reliability that needs to do that. Recently worked on a site where the operations department, when we went to kind of validate the cost of downtime, couldn't really tell us. Changed from day to day or week to week. And from an organizational perspective, it's very hard to make decisions if you haven't defined that. And in reliability, we need that downtime number to justify holding spares or justify doing tasks. And if operations hasn't defined that, then I think reliability is the perfect person to facilitate that discussion.
Great. Got a quick couple more that are keeping on flowing in, Joel. One from Dean is, how do you account for imperfect repairs impact, i.e. managing this parameter in conjunction with stores or assume perfect repairs? Similar observation with environmental or conditions of use. Not sure if that, you can answer that now, or we need to take it offline, Joel?
No, I think I can. We didn't cover that aspect in detail, or we didn't cover it at all actually, but there, you would have noticed as I'm switching through the program, there are a couple of boxes, hidden that we didn't go over in detail, and one of those boxes is repairs, bring it back to as good as new. So the assumption there that we made in this particular example is that you put a new spare part in and you make that repair, and you're now way back up on the failure curve, it's as good as new. One of the options we have is also as good as old, which means it doesn't do anything in terms of renewing the life. And then there's an intermediary option that says it puts it somewhere in the middle, and we can define what that is, whether it's 50% or 75%. So from a modeling perspective, we can say that the repair done didn't necessarily increase its full life.
Correct.
So I think that's kind of what that question is getting after.
Yep. And got one more that we're going to get to. How would you manage insurance spare parts when they are not used?
I guess that was kind of the intention of what we talked about today. So most of what I went over would be specific to insurance spare parts. So things that you just keep around in case of a failure, in case of a potential failure. So, the intention of what we went over today was mainly to address those insurance spares that aren't needed as part of a PM routine, but are just there in case.
Correct. Got a few more keeping on coming in. We'll keep going if that's all right, Joel. One from Erwin is, what should be the factors to be considered in order to assess the criticality of a spare part?
That's a very good question. I think what I would do is go back to our slide where we talked about the different things that make up a spare part. So we have done kind of a flow chart type process before that says, in terms of factors, how much does a spare part cost? What's the lead time? What impact does it have on production? What other areas of the facility is it used in? So kind of the answer to some of those questions and the answer to some of those factors would then push you into doing a different level of analysis. And we've even set it up before to say those factors are variables that can change. So you can answer the questions for all of your spare parts and then kind of look at the distribution of where the spare parts lie. So for example, I mentioned that you might want to target 10% of your most critical spares and do a more detailed level of analysis on it. So you can actually change the range of those variables to push the spare parts into different criticality buckets. They may all have the same ranking top to bottom, but they would fall in different buckets based on those variables that you chose. So for example, any spare part that costs more than $100,000, you push towards this quantitative analysis, and anything less than that, you do a lower level of analysis.
Great. All right, we're going to do one more, Joel, and then I will call it a day. There are a lot of questions flowing in. If your question hasn't been answered, I've got a record of them, and we will get you an email, an answer to those questions via email. But the last one for today is, Joel, how can I add up the spares requirements when we have more than one piece of equipment with the same spare item but different functions in the operation, and then still get the best inventory level?
Okay, so if I understand it correct, they're the same spare part, but they're being used in different parts of the operation, so they might have different repair times, and probably most importantly, different life.
Correct, and different functions, yep.
Different functions, yeah, so different wear rates, for example. So I mentioned some of the different modules available within Availability Workbench, and RCM cost kind of works well for the type of analysis I was doing, but that's the same operating context, right? If we want to look at optimizing different operating contexts for one spare part, that's probably where we would switch over to the AVSIM module within Availability Workbench. And when we do that, it takes more of a holistic system approach. We can bring in capacity and look at how that affects it. So we might have one spare part with a certain capacity and another spare part that doesn't affect the capacity as much as the other one. So we can do a little bit more complex spare part optimization, and that's probably where I would bring it into AVSIM and do the spare parts analysis in that module.
Great. Excellent. Thanks, Joel. One question which I'll ask that Deepak has asked is, does ARMS reliability offer training and workshops in the 5 pillars of the SMRP, the body of knowledge for the CMRP? And that answers yes, and Deepak, and I'll get you some more information on that. So just to close out today, a big thanks to Joel for presenting on this topic. All the attendees, you will get a copy of the slide deck and some more information on spares following this via email. If you have any more questions, you can reach out to Joel directly. His info is on the screen. Or reach out to ARMS Reliability through our website. More than happy to take individuals through a little more detail in this. And then we've also brought in existing FMEA models or RCM models that you may have and show you how the tool and our methodologies can apply some of this spare parts work that Joel showed you today to hopefully bring some benefits to your organization. So if you want some more details, please reach out to Joel. We'll be happy to show you and have a chat with you about how we might be able to help your individual organization's reliability and maintenance needs. On that note, thanks everyone for attending, and enjoy the rest of your Thursday.
All right, thanks everyone. Bye.